The textbook readings for Chapter 5 and 7 are no longer than any of the other assigned weekly readings in the book. However, the slide presentation is the longest in the series, and the reason for that is I've tried to design this to assist students in understanding the concepts here, because generally they have more problems understanding the material in these two chapters. Now, in Chapter 5, we'll discuss data and process modeling techniques that analysts use to show how the system takes data and transforms it into useful information. The deliverable or end product of the data and process modeling is actually what we'll call a logical model as opposed to a physical model that will support business operations and meet users' needs. The difference between a logical model and a physical model is pretty straightforward. A logical model shows what the system has to do, regardless of how it will be implemented physically. Later in the system's design phase, we'll build the physical model that describes how the system will be constructed. Data and process modeling involves three main tools. The first is data flow diagrams, the second, the data dictionary, and third, process descriptions. A data flow diagram, or DFD, uses various symbols to show how the system transforms the input data into useful information. Other graphical tools include object models, which are explained in Chapter 6 of the text, but which we will not cover during this course, and the entity relationship diagrams, which are described in Chapter 9 in the data design section of the course. As I've indicated here, a data flow diagram shows how data moves through an information system, but does not show program logic or the processing steps. A set of DFDs provides a logical model that shows what the system does, not how it does it. That distinction is important because focusing on implementation issues at this point would restrict our search for the most effective system design. Data flow diagrams use four basic symbols that represent processes, data flows, data stores, and entities. Several different versions of DFD symbols exist, but they all serve the same purpose. The slide you're looking at gives examples of what are called the Gain and Saracen symbol set on the top, and another popular symbol set on the bottom is the Jordan symbol set. Symbols are referenced by using all capital letters for the symbol name. A process symbol receives input data and produces output that has a different content, form, or both. Processes contain the business logic, also called business rules, that transform that data and produce those required results. The symbol for a process is a rectangle with rounded corners. The name of the process appears inside the rectangle. The process name identifies a specific function and consists of a verb and an adjective if necessary, followed by a singular noun. For example, some processes are apply rent payment, calculate commission, assign final grade, verify order, fill order. Processing details aren't shown in the DFD. For example, you might have a process named deposit payment. The process symbol doesn't reveal the business logic for the deposit payment process. To document the logic, you'll create a description which will be explained later in this chapter. In data flow diagrams, a process symbol can be referred to as a black box because the inputs, outputs, and general functions of the process are known, but the underlying details and the logic of the process are hidden. By showing processes as black boxes, an analyst can create DFDs that show how the system functions, but at this point they can avoid all the unnecessary detail and clutter. A data flow is a path for the data to move from one part of the information system to another. A data flow in a DFD diagram represents one or more data items. For example, a data flow could consist of a single data item, such as student ID number, or it could include a set of data, such as class roster, with student ID numbers, names, registration dates for the specific class, etc. Although the DFD does not show the detailed contents of a data flow, that information is included and recorded in the data dictionary, which we'll talk about later in this chapter. The symbol for a data flow is a line with a single or double arrowhead. The data flow name appears above, below, or alongside the line. A data flow name consists of a singular noun and an adjective if needed. Examples of data flows to the left here are deposit, invoice payment, student grade, order, and commission. Now, a process symbol can have more than one outgoing data flow. That's shown in the graduate student work process, or more than one incoming data flow as shown in the calculate gross pay process. A process can also connect to any other symbol, including another process symbol, as shown by the connection between verify order and assemble order. A data flow, therefore, must have a process symbol on at least one end. Now, for a minute, turn to page 203 in your book. There's a diagram, figure 5-6, that shows 3 data flow and process combinations that you must avoid. The first is called spontaneous generation. In the diagram in the book, the apply insurance premium process, for instance, produces an output that has no input data flow. Because it has no input, the process is called a spontaneous generation process. There's also a black hole, not to be confused with the black box. A black hole, the calculate gross pay, is called a black hole process, which is a process that has an input but doesn't produce any output. And then finally, there is a gray hole, and that's a process that has at least one input and one output, but the input is obviously insufficient to generate the output shown. For example, again, in the diagram in the book, a date of birth input is not sufficient to produce a final grade output in the calculate grade process. Spontaneous generation, black hole. Another key data flow diagram symbol is that for a data store. It's used to represent data that the system stores because one or more processes need to use that data at a later time. For instance, instructors need to store student grades on tests and assignments during the semester so that they can calculate and assign final grades at the end of the term. The physical characteristics of a data store are unimportant because you're concerned only here with a logical model. Also, the length of time the data is stored is also unimportant. It could be a matter of seconds while a transaction is processed, or it could be a period of months while the data is accumulated for year-end processing. What is important is that a process needs access to the data at some later time. Before we can begin constructing DFD diagrams, there is one more symbol that we have to understand, and that is the entity symbol. The symbol for an entity is a rectangle, which may be shaded to look like it's three-dimensional. The name of the entity appears inside the symbol. A DFD shows only external entities that provide data to the system or receive output from the system. A DFD shows the boundaries of the system and how the system interfaces with the outside world. DFD entities are also called terminators because they're the data origins or final destinations. Systems analysts call an entity that supplies data to the system a source, and an entity that receives data from the system a sink. An entity name is the singular form of a department, an outside organization, other information system, or person. An external entity can be a source or a sink or both, but each entity must be connected to a process by a data flow. With this understanding of the proper use of DFD symbols, we're ready to construct diagrams that use these symbols. Creating a set of DFDs. During the requirements modeling, we used interviews, questionnaires, and other techniques to gather facts about the system. And we learned how the various people, departments, data, and processes all fit together to support business operations. Now we're ready to create a graphical model of the information system based on our fact-finding results. But first, we're going to review a set of guidelines for drawing DFDs. Then we'll go into how to apply these guidelines and create a set of DFDs using a three-step process. In creating a set of DFDs, there are several guidelines for the actual drawings that you need to be aware of. When you draw a context diagram or other DFD, you should follow these guidelines. Draw the context diagram so that it fits on one page. Use the name of the information system as the process name in your context diagram, and also use unique names within each set of symbols. Continuing with our guidelines, don't cross lines. Provide a unique name and a reference number for each process, and obtain as much user input and feedback as possible. Your main objective here is to ensure that the model is accurate, easy to understand, and meets the needs of the users. In creating a set of DFDs, your first step is to draw a context diagram. A context diagram is the top-level view of an information system that shows the system's boundaries and scope. To draw a context diagram, you start by placing a single process symbol in the center of the page. The symbol represents the entire system, and you identify it as process 0, the number 0, not the letter O. Then you place the system entities around the perimeter of the page and use data flows to connect the entities to the central process. Now, data stores are not shown in the context diagram because they're contained within the system and remain hidden at this level, but they will appear in when we create the more detailed diagrams. I know that these two diagrams are a little bit blurry, and I apologize for that, but I think you can see what you need to see here. In the previous step, you learned that a context diagram provides the most general or top-level view of an information system, and it contains a single process symbol which is like a black box. To show the detail inside the black box, you create DFD Diagram 0. Diagram 0 zooms in on the system and shows the major internal processes, data flows, and data stores. Diagram 0 also repeats the entities and data flows that appear in the context diagram. When you expand the context diagram into DFD Diagram 0, you must retain all the connections that flow into and out of process 0. Shown here, we have a context diagram on the left and a diagram 0 on the right for the grading system. Because diagram 0 is an exploded version of process 0, it shows considerably more detail than the context diagram does. You can refer to diagram 0 as a partitioned or decomposed view of process 0. When you explode a DFD, the higher level diagram is called the parent diagram, and the lower level or more detailed diagram is referred to as the child diagram. When you create a set of DFDs for a system, you break the processing logic down into smaller units which are called functional primitives that the programmers will use to develop the actual code. A functional primitive is a process that consists of a single function that can't be exploded any further. In step 3, we're ready to begin drawing the lower level diagrams. To create a lower level diagram, you must use leveling and balancing techniques. Leveling is the process of drawing a series of increasingly detailed diagrams until all the functional primitives are identified. Balancing maintains consistency among a set of DFDs by ensuring that both the input and output data flows align properly. Leveling and balancing are described in this and the following slide. Leveling uses a series of increasingly detailed DFDs to describe an information system. For example, a system might consist of dozens or even hundreds of separate processes. Using leveling, an analyst starts with an overall view, which is the context diagram, with a single process symbol. Next, the analyst creates a diagram 0, which shows more detail. The analyst continues to create lower-level DFDs until all the processes are identified as functional primitives. This represents a single process function, as we talked about. More complex systems have more processes, and analysts have to work through many levels to identify the functional primitives. Leveling is also called exploding or partitioning or decomposing. In our drawing to the left here, we took the process 0 symbol that had 2 input flows and 2 output flows, and we exploded that into the next level of detail. Now, 3 processes, 2 data stores, and 4 internal data flows are visible. Notice that the details of process 0 are shown inside a dashed line, just as if you could see the whole process. We can say that this DFD is balanced because the 4 data flows into and out of process 0 have been maintained on the child DFD. The DFDs are also leveled because each internal process is numbered to show that it's a child of a parent process. As we've already indicated, a set of DFDs produces a logical model of the system, but the details within those DFDs are documented separately in a data dictionary, which is the second component of structured analysis. A data dictionary, or data repository, is the central storehouse of information about the system's data. An analyst uses the data dictionary to collect, document, and organize specific facts about the system, including the contents of the data flows, the data stores, the entities, and the processes. The data dictionary also defines and describes all data elements and meaningful combinations of data elements. A data element, also called a data item or a field, is the smallest piece of data that has meaning within an information system. Significant relationships exist among the items in the data dictionary. Data flows are connected to data stores, entities, and processes. Accurately documenting these relationships is essential so that the data dictionary is consistent with the data flow diagrams. In order to achieve this, you can also use case tool software, which will help you document the design as you're going through the process. I can tell you from experience that the more complex the system, the more difficult it is to maintain full and accurate documentation. Fortunately, modern case tools greatly simplify this task. For example, in the Visible Analyst case tool, documentation automatically flows from the modeling diagrams into the central repository, along with the information entered by the users. A case tool repository ensures that the data consistency, which is especially important where multiple systems require the same data. You have to document every data element in the data dictionary. Now, some analysts like to record their notes online or in manual forms. Others prefer to enter the information directly into the case tool. I'm in that latter category. My preference is to enter that information straight into the case tool. Several of the DFDs and data dictionary entries that appeared in your text and also in the slide presentation were created using the Visible Analyst case tool. Other case tools might use other terms, they might display the information slightly differently, but the objective is the same. It's to provide a clear, comprehensive set of information about the data and the processes that make up the system. Several of the DFDs and the data dictionary entries that appear in the chapter and also in the slide presentation were created using the Visible Analyst case tool. Although other case tools might use other terms or display the information differently, the objective is the same, to provide a clear, comprehensive information about the data and the processes that make up the system. Regardless of the terminology or method that's used, the following attributes usually are recorded and described in the data dictionary. The data element or name label. The data element standard name, which would be meaningful to users, and this is consistent throughout the system. An alias is simply any other name that other than the standard data element name that's an alternative. That's called an alias. For example, for Social Security, we all refer to it as SSN. SSN would be the alias. Type and length refers to whether the data element contains numeric, alphabetic, or character values, and the length is the maximum number of characters for an alphabetic or character data element, or the maximum number of digits and number of decimal positions for a numeric element. In the example on the previous page, 9N would indicate under Social Security number that there are 9 characters, all numeric, in the field. Take note that when it says 9N, that by definition eliminates any dashes in the Social Security number. Next we have default value, and that is the value for the data element if a value otherwise is not entered for it. And sometimes that can be null. Acceptable values, this specifies the specification of the data element's domain, which is the set of values permitted for that data element. The values can be specifically listed in a reference table, or they can be selected from a specified range of values. You would also indicate if a value for the data element is optional. Some data elements have additional validity rules. For example, an employee's salary must be within a range defined for the employee's job classification. Next is the source. This is the specification for the origination point of the data element's values. The source could be a specific form within the system, a department, or an outside organization, another information system, or it could be the result of a calculation. Security identifies the individual or department that has access or update privileges for each data element. For example, only the credit manager has the authority to change a credit limit, while sales reps might be authorized to access data in a read-only mode. Responsible users is identification of the users responsible for entering and changing the values for this data element. Then the description and comments. This part of the documentation allows you to enter any additional notes you may have gathered. Documenting data flows is very similar. In addition to documenting each data element, you must also document all the data flows in the data dictionary. Although the terms can vary, typical attributes are as follows. Data flow name or label. That's the data flow name as it appears on the DFDs. The description simply describes the data flow and its purpose. Alternate names are any aliases for the DFD. The origin. Where did the DFD begin? What's its source or data flow? The origin can be a process, it can be coming from a data store, or an entity. Destination. The DFD's ending point for the data flow. The destination can be a process, again, a data store, or an entity. Record. Each data flow represents a group of related data elements called a record or data structure. In most data dictionaries, records are defined separately from the data flows and data stores. When records are defined, more than one data flow or data store can use the same record if necessary. And finally, we have volume and frequency. This describes the expected number of occurrences for the data flow per unit of time. In the data dictionary, you must also document the data stores. Some of the typical characteristics used for describing a data store are shown on this slide. Your data dictionary documentation also includes a description of the processes. That would be the process's characteristics, and for the functional primitives, process description, which is a model that documents the processing steps and the business logic. On the remainder of this slide, I show the typical characteristics of a process. By documenting all entities, the data dictionary can describe all external entities that interact with the system. The typical characteristics for an entity are those that I've shown on the rest of this slide. A record is a data structure that contains a set of related data elements that are stored and processed together. Data flows and data stores consist of records that you must document in the data dictionary. To define the characteristics of each of those records, you would use the characteristics I have indicated on this slide. As we've already indicated, the data dictionary serves as a central storehouse of documentation for an information system. A data dictionary is created when the system is developed, and it's updated constantly as the system is implemented, operated, and maintained. In addition to describing each data element, data flow, data store, record, entity, and process, the data dictionary documents the relationships among all those components. You can obtain many valuable reports from a data dictionary. I've given you some examples on this slide. Using a set of process description tools, you can create a model that's accurate, complete, and concise. Typical process description tools include structured English decision tables, decision trees. You're probably familiar with decision tables and decision trees, but structured English might be a new concept to you. When you analyze a functional primitive, you break the processing steps down into smaller units in a process that is called modular design. Modular design is based on combinations of three logical structures, also referred to as control structures, which serve as building blocks for the process. Each logical structure must have a single entry and exit point. The three structures are called sequence, selection, and iteration. Sequence is the completion of steps in a sequential order, one after another. One or more steps might represent a subprocess that contains additional logic structures. Selection is the completion of one or two more process steps based on the results of a test or a condition. An iteration is the completion of a process step that is repeated until a specific condition changes or is met. An example of iteration is a process that continues to print paychecks until it reaches the end of the payroll file. Iteration is also referred to as looping. Sequence, selection, and iteration structures can be combined in various ways to describe processing logic. Structured English is a subset of standard English that describes logical processes clearly and accurately. When you use structured English, you need to conform to the rules I've outlined on this table and that are also defined in your book. Structured English can help make your process descriptions accurate and understandable to users and system developers. Structured English might look familiar to programming students because it does resemble pseudocode, which is used in program design. The techniques are similar, but the primary purpose of structured English is to describe the underlying business logic, while programmers who are concerned with coding mainly use pseudocode as shorthand notation for the actual code. A decision table is a logical structure that shows every combination of conditions and outcomes. Analysts often use decision tables to describe a process and ensure that they've considered all the possible situations. Decision tables are easy to create. You can do them in Microsoft PowerPoint, Word, Excel, and I would hope, I'm not going to spend too much time on decision tables and decision trees because by this point in your career, I would hope that you are already familiar with these two concepts. Pages 226 through 229 in your text do an exceptionally good job of explaining how to construct and use decision tables. The only thing I would add that is decision tables are often the best way to describe a complex set of conditions. Many analysts use decision tables because they are easy to construct, they're easy to understand, and programmers find them easier to work with when they're trying to develop the code. A decision tree is a graphical representation of the conditions actions, and rules found in a decision table. Decision trees show the logic structure in a horizontal form that resembles a tree with the roots at the left and the branches to the right. Similar to flowcharts, decision trees are useful ways to present the system to management. Decision trees and decision tables provide the same results, but in different forms. In many situations, a graphic is the most effective means of communications. Whether you use a decision tree or a decision table is often just a matter of personal preference. A decision table might be a better way to handle complex combinations of conditions. On the other hand, a decision tree is an effective way to describe a relatively simple process. On this slide and the two that follow it, I've tried to provide you a quick overview of the things that we have talked about in this chapter. Take the time to look at these points and make sure that you understand them. If you don't, refer back to the text, read through it again before you move on to Chapter 7 so that you have a good understanding and a good basis for the next bit of material that we're about to present. Remember that DFDs use 4 symbols. The process symbol transforms data. The data flow symbol shows data movement. The data store symbol shows data at rest. And the external entity symbol represents someone or something connected to the information system. Various rules and techniques are used to name, number, arrange, and annotate the set of DFDs to make them consistent and understandable. We talked quite a bit about the data dictionary and the importance of documentation in general. If there is one area in the IT world that I would say universally should be adhered to more closely, it is that of documentation. So when you do your systems analysis, make absolutely certain that you document everything at each step along the way. The better you document, the happier you'll be with yourself as you go further in the project. Chapter 7 is the final chapter in the systems analysis phase of the software development lifecycle. This chapter describes software trends, acquisition and development strategies, traditional versus web-based development, outsourcing versus in-house development, the systems requirement document, prototyping, and preparing for the transition to the next software development lifecycle phase, which is system design. Just a few years ago, a typical company either developed software itself, purchased a software package called off-the-shelf, or hired consultants or used inside resources to perform the work. Today, a company has many more choices, including application service providers, web-hosted software options, and firms that offer a variety of enterprise-wide software solutions. Selecting the best development path is an important decision that requires companies to consider 3 key topics: the impact of the Internet, software outsourcing options, and in-house software development alternatives. The next few slides review each of these 3 in some detail. In the traditional model, software vendors develop and sell application packages to customers. Typically, customers would purchase licenses. Keep in mind, you never really own your software. You're basically renting it. But the software license gives them the right to use the software under the terms of the license agreement. That model still accounts for most software acquisition, but there's a new model called Software as a Service, or SaaS, that's changing the picture very significantly. Software as a Service is a model of software development where an application is hosted as a service provided to customers over the Internet. Software as a Service reduces the customer's need for software maintenance, operation, and support. This is particularly attractive to smaller companies who, for example, might not have the internal IT resources that a larger company enjoys. As a systems analyst, you have to consider whether development should take place in a web-centric framework or in a more traditional environment. Although there is a major trend toward web-based architecture, many firms rely on traditional systems, either because they are legacy applications that are not easily replaced, or because they don't need a web component to satisfy user needs. If you have to choose, you should consider some key differences between the traditional and the web-based system development. Building the application in a web-based environment can offer greater benefits and sometimes greater risks compared to the traditional environment. The previous slide described the traditional development environment. Now we're going to take a look at the web-based development environment. In addition to the 2 bullet points indicated on this slide, some things to keep in mind are that internet-based development treats the web as a platform rather than just a communications channel. Also, web-based software treats the software application as a service that is less dependent on desktop computing power and resources. However, there's a downside. If you are using a web-based system, keep in mind you must be connected to the web in order to use your own system. Another consideration is that web-based software usually requires additional layers called middleware to communicate with your existing software and your legacy systems. Outsourcing is the transfer of information systems development, operation, or maintenance to an outside firm that provides those services for a fee on a temporary or a long-term basis. Traditionally, firms outsourced IT tasks as a way of controlling costs and dealing with rapid technological change. Those are still valid reasons for outsourcing, but it has become an overall part of IT strategy for many organizations. The outsourcing trend also has affected software vendors who have adjusted their market accordingly. A firm that provides outsourcing solutions is called a service provider. 2 popular outsourcing options involve application service providers and firms that offer internet business services. Application service providers, there are firms that deliver software applications or access to an application by charging either a usage or a subscription fee. An ASP provides more than just a license to use the software. It rents an operational package to the customers. ASPs represent a really rapidly growing trend using the internet as the primary delivery channel. Now, internet business services firms provide a powerful web-based support for transactions such as order processing, billing, customer relationship management. An IBS solution is attractive to customers because it offers online data center support, mainframe computing power for mission-critical functions, and universal access via the internet. We're also, IT is a constantly changing world, and no area is more dynamic than internet technology. A couple of the evolving trends are Web 2.0 and cloud computing. Systems analysts need to be aware of these concepts and consider them as they plan large-scale systems. Web 2.0 and cloud computing are discussed in much greater detail in Chapter 10, System Architecture, so we won't dwell on those here. Before we move on, let's just return to outsourcing for just a minute. Firms that offer software as a service rather than a product have developed fee structures that are based on how the application is used by customers during a specified time period. Several models exist, including fixed fee, subscription, and usage or transaction. A fixed fee model uses a set fee based on a specified level of service and user support. An example of a fixed fee model is Oracle's on-demand service. A subscription model has a variable fee based on the number of users or workstations that have access to the application. And finally, a usage model or transaction model charges a variable fee based on the volume of transactions or operations performed by the application. When a company decides to outsource IT functions, it takes an important step that can affect the firm's resources, operations, and profitability. Mission-critical IT systems should only be outsourced if the result is a cost-attractive, reliable business solution that fits into the company's long-term business strategy and involves an acceptable level of risk. Moving IT work overseas raises even more issues, including potential concerns about control, culture, communications, and security. And we'll talk more about that in just a minute. Outsourcing can be especially attractive to a company whose volume fluctuates widely, such as a defense contractor. In other situations, a company might decide to outsource application development tasks to an IT consulting firm if the company lacks the time or expertise to handle the work on its own. Outsourcing relieves a company of the responsibility of adding IT staff in busy times and downsizing when the workload lightens. A major disadvantage, though, of outsourcing is that it does raise employee concerns about job security. Talented IT people usually prefer positions where the firm is committed to in-house IT development. If they don't feel secure, they may, as we say, decide to find their happiness elsewhere. Offshore outsourcing, or global outsourcing, refers to the practice of shifting IT development, support, and operations to other countries. In a trend similar to the outflow of manufacturing jobs over a several decades long period, many firms are sending their IT work overseas at an increasing rate. In addition to exporting IT jobs, many large multinational firms, including Microsoft and IBM, have opened technical centers in India and other countries. Some observers believe that India might gain as many as 2 million IT jobs in the next decade. The main reason for offshore outsourcing is the same as domestic outsourcing: lower your bottom line costs. Offshore outsourcing, however, involves some unique risks and concerns. For example, workers, customers, shareholders, and some companies have protested this trend and have raised public awareness of the possible economic impact. Even more important, offshore outsourcing involves unique concerns regarding project control, security issues, disparate cultures, and effective communication with critical functions that might be located halfway around the world. In addition to numerous outsourcing options, a company can also choose to develop its own systems or purchase and possibly customize and implement a software package. Although many factors influence this decision, the most important consideration is the total cost of ownership, which we talked about in Chapter 4. Now, the choice between developing versus purchasing software is called the make or buy, build or buy decision. The company's IT department makes, builds, and develops in-house software, or a software package is obtained from a vendor or application service provider. With a wide variety of software packages available to handle the business operations, why would a firm choose to develop its own software? Typically, companies choose in-house development to satisfy unique business requirements, or to minimize changes in business procedures and policies, or to keep constraints of existing systems and existing technology to meet those constraints, and to develop internal resources and capabilities. If a company decides not to outsource, a commercially available software package might be an attractive alternative to developing its own software. The advantages of purchasing a software package over developing software in-house include lower costs, less time to implement a system, proven reliability and performance benchmarks, less technical development staff, future upgrades are provided by the vendor, and the ability to obtain input from other companies who already have implemented the software. All of these are critical factors. If the standard version of a software product doesn't satisfy a company's requirements, the firm can consider adapting the package to meet its needs. There are basically 3 ways to customize a software package. First, you can purchase the basic package that the vendors will customize to suit your needs. A vendor almost always offers options when their standard package won't satisfy all their customers. 2, you could negotiate directly with the software vendor to make enhancements to meet your needs by paying for the changes. Or 3, you can purchase the package and make your own modifications if this is permissible under the terms of the software license. A disadvantage to this approach is that systems analysts and programmers might be unfamiliar with the software, and they're going to need time to learn the package and make the modifications correctly. Additionally, some advantages of purchasing a standard software package disappear if the product has to be customized. Business requirements sometimes can be fulfilled by a user application rather than a formal information system or a commercial package. A user application utilizes a standard business software such as Microsoft Word or Excel that has been configured in a special manner to enhance user productivity. Many companies also empower lower-level employees by providing more access to data and more powerful data management tools. The main objective here is to allow lower-level employees more access to the data they require to perform their jobs with no intervention from the IT department. Empowerment reduces costs and makes good business sense, but companies that adopt this approach must provide the technical support that empowered users will require. In most large and medium-sized companies, a help desk or information center within the IT department is responsible for providing this user support. Once they learn an application, many users can perform tasks that once required a programmer. Some examples, some user applications have very powerful screen generators and report generators, and these allow the users to design their own data entry forms and reports. At some point in the systems development process, the company has to decide whether to use an outsourcing option, to develop the software in-house, acquire a software package, develop user applications, or select some combination of these solutions. That decision will affect the remaining software development lifecycle phases and your investment as a systems analyst. The evaluation and selection of alternatives is not a simple process. The objective is to obtain the product with the lowest total cost of ownership, but actual cost and performance can be difficult to forecast. With a large number of choices, then, how do you select the best alternative? When selecting hardware and software, systems analysts often work as an evaluation and selection team. A team approach ensures that critical factors are not overlooked and that a sound choice is made. The evaluation and selection team also must include users who will participate in the selection process and feel that sense of ownership in the new system that we've talked about previously. Part C of the Systems Analyst Toolkit, which we went through extensively last week, explains how to use the three main cost analysis tools: payback analysis, return on investment, and net present value. Just as a quick review, we'll say the following. Payback analysis determines how long it takes an information system to pay for itself through reduced costs and increased benefits. Return on investment is a percentage rate that compares the total benefits or return received from a project to the total costs investment in the project. The net present value of a project is the total value of the benefits minus the total costs, with both costs and benefits adjusted to reflect the point in time at which they occur. The best way to use those three tools is really to develop a cost-benefit checklist with the steps I've outlined on this slide. In your cost-benefit analysis checklist, what you will do with it is you'll analyze the various software license options, including fixed fees and formulas based on the number of users and transactions. And you'll also apply the financial analysis tools we just discussed to each one of those alternatives. Then you'll take a look at the results, prepare a report to management, and from that you'll probably also make a recommendation. And from that they will then make the decision on which way to proceed. On this slide, we'll very briefly go through the software acquisitions process. There are 6 steps in general in this process, and this will vary from company to company. Step 1 is evaluate the information system requirement. Based on your analysis of the system requirements, you have to identify the system's key features. You'll have to consider network and web-related issues, estimate the volume and future growth, specify any hardware, software, personnel constraints, and prepare a request for proposal or quotation. Step 2 is identify the potential vendors or outsourcing options. The internet is the primary marketplace for all IT products and services, and you can find descriptive information on the web about all the major products and the acquisition alternatives themselves. Step 3 shouldn't need any explanation. It's time now to evaluate your alternatives, and you should have multiple alternatives. Don't go forward with one recommendation, one suggestion. Don't put yourself in the position that if the management says, don't like that, what else you got? You don't have anything. Step 4, perform a cost-benefit analysis. We've been through that in depth. And 5 is prepare a recommendation. And you should prepare a recommendation that evaluates and describes the alternatives together with the cost, benefits, advantages, and disadvantages of each option. At this point, you may actually be required to submit a formal systems requirement document and deliver the presentation. And then, of course, step 6 is to implement your solution. Remember that the systems requirements document is the culmination of the entire systems analysis phase. The system requirements document is like a contract that identifies what systems developers must deliver to the users. Recall that systems requirements are identified during the fact-finding process, and a systems requirement checklist was created back at that time. Now, because the system requirements document can be lengthy, you should format and organize it so that it's easy to read and use. The system requirements document should include a cover page and a detailed table of contents. You can also add an index and glossary of terms to make the document easier to use. The content of the systems requirement document will depend on the company and the complexity of the system that you're proposing. The presentation to management at the end of the systems analysis phase is one of the most critical milestones in the system development process. At this point, managers make key decisions that will affect the future development of the system. Prior to the management presentation, you might give 2 other presentations. One to the principal individuals in the IT department to keep them aware of what you're going to be presenting, and another presentation to users to answer their questions and invite feedback. The system requirements document is the basis for all 3 presentations, and you should distribute the document, or at least a summary, in advance so that the recipients can review it. The objective of the management presentation is to obtain approval for the development of the system and to gain management's full support, including the necessary financial resources. As a result of your presentation, management will have to make one of the 5 decisions shown on this slide. After the presentation and the management decision, you'll begin to work on a transition to the systems design phase of the software development lifecycle. If you're developing an in-house system or you're modifying a package, you will build a model of the proposed system and start designing the system's output, input, files, and data structures. In a traditional software development lifecycle environment, systems design usually started when the systems analysis phase was done. Using the system requirements specification as a blueprint, the developers transformed the logical design into a working model that could be tested, reviewed by users, and implemented. Today, however, that process is much more dynamic. In general, systems development is faster, more flexible, and more user-oriented. The introduction of adaptive methods such as agile development and extreme programming has changed the landscape. Depending on the project, system developers often blend traditional and cutting-edge development methods because what works in one situation might not work in another. Regardless of the development method, systems design requires accurate documentation. You will have laid out a logical design which defines what must take place in the system, not how it will be accomplished. The logical designs don't address the actual methods of implementation. In contrast, the physical design is like a set of blueprints for actual construction of a building. Typically, physical design describes the actual process of entering, verifying, storing the data, the physical layout of the data files, and sorting procedures, the format, and so on. But because both the logical and the physical designs are related so closely, Good systems design is impossible without a careful, accurate analysis. Because the components of a system are interdependent, the design phase is not a series of clearly defined steps. Although you might start in one area, you could find yourself working with several different elements at the same time. For example, decision to change a report format might require changes in the data design or the input screens. Your design checklist will include the user interface, input and output procedures, data design, and system architecture. The final steps are to prepare a systems design specification and present those results to management. The goal of systems design is to build a system that satisfies the business requirements. Although each project is different, design considerations usually involve users, data, and system architecture. Under user considerations, the most important goal is to make the system user-friendly. Here are some suggestions to keep in mind. Under the carefully consider any point where users receive input or output, the user interface must be easy to learn. Input processes should be easy to follow, intuitive, and forgiving of errors, and output should be attractive and easy to understand with an appropriate level of detail. Anticipate future needs shouldn't need much explanation. Many of you probably remember the Y2K issue, where there was a huge concern that when some older programs that used only 2 characters to store the year might not adjust properly to the new century, and the fear was that many systems would shut down. Flexibility is also a key issue. Suppose that a user wants a screen to display all customer balances that exceed $5,000 in an accounts payable system. Well, a programmer could easily program that, but that's inflexible. For instance, if a user later needs a list of customers whose balances exceed $7,500 rather than $5,000, more programming would be needed. A better approach might be to allow the user to enter the amount, and that's called a parameter. A parameter is a value that the user enters whenever the query is run, which provides flexibility, enables the users to access the information easily, and costs less. A good systems design can combine both approaches. For example, you could design the program to accept a variable amount entered by the user, but it could start with a default value, in this case $5,000, that the system displays automatically. The users could simply press enter to accept the default value or enter the parameter. Data entry and storage are important in every system. On this slide, I have put some suggestions for you to keep in mind in those areas. Each of these is fairly self-explanatory and shouldn't require much explanation. If you do need a little more explanation, you'll find it in the text on pages 313 and 314. Under the category of architectural considerations, there are 2 things that you should take into consideration. The first is to use a modular design. In a modular design, you create individual components called modules, which connect to a higher level program or process. In a structured design, each module represents a specific process, which is shown on a DFD and documented in the process description. You also want to design modules that perform a single function, and here's why. Independent modules provide greater flexibility because they can be developed and tested individually. Then they can be combined or reused later in the development process. Modular design is especially important in designing large-scale systems because separate teams of analysts and programmers can work on different areas and then integrate the results. You're going to find that design goals often conflict, and you have to consider alternatives and trade-offs. Most trade-off decisions that you're going to face are going to come down to 2 basic issues: quality versus cost. Although every project has a budget and financial constraints, you should avoid decisions that achieve short-term savings but might mean higher costs later. For example, if you try to reduce implementation costs by cutting back on system testing or user training, you can create higher operational costs in the future. If necessary, you should document and explain the situations carefully to management and discuss the possible risks. Each trade-off must be considered individually, and the final result has to be acceptable to the users, the system staff, and to company management. Earlier in our discussion about rapid application development, we introduced the concept of prototyping. There are several different kinds of prototyping that might be used, and you could use all of them in any given project. The first is system prototyping. This produces a full-featured working model of the information system. Systems analysts also use prototyping, though, to verify user requirements, after which a prototype is discarded and the implementation continues. This approach is called design prototyping or throwaway prototyping. In this case, the prototyping objects are more limited than they were in the systems prototyping, but they're no less important. The end product of design prototyping is a user-approved model that documents and benchmarks the features of the finished system. Whenever possible, you should allow users to experiment with a prototype and provide feedback on how well it meets their needs. This approach can increase development costs, but the expense will be offset by lower costs during the subsequent phases of the software development lifecycle. Although most systems analysts believe that the advantages of prototyping far outweigh the disadvantages, you should also consider the following potential problems. The rapid pace of development can create quality problems which won't be discovered until the finished system is operational. Also, other systems requirements such as reliability and maintainability can't be adequately tested using a prototype. And in very complex systems, the prototype can become unwieldy and difficult to manage. Most prototyping is done using case tools, application generators, report generators, screen generators, and fourth-generation languages. In a fourth-generation language, you'll remember, the commands tend to resemble natural statements that people use. In combination, the tools provide a framework for rapid, efficient software development called a fourth-generation environment. You'll remember that in Part B of the Systems Analyst Toolkit, we went into great detail about case tools. We explained how the systems analysts use them and how they speed up development processes, reduce costs, and avoid design errors. Prototyping does have its limitations. The final version of a system typically demands a higher level performance than a prototype can provide. A prototype is a functioning system, but it is less efficient than a fully developed system. And because it's a model rather than a completed system, the prototype will have slower processing speeds and response times. Also, the prototype might lack the security requirements, exception and error handling procedures, and other required functions. Despite those limitations, systems developers can upgrade a prototype into the final information system by adding in that capability. Even when it does not evolve into a finished system, a prototype helps to ensure that the final project will meet all requirements. Satisfying system requirements is the ultimate goal of systems development, and prototyping is an extremely valuable tool during that process. In Chapter 7, we described the systems development strategies, preparation for presentation and systems requirements document, and the transition to the design phase. We talked about software as a service and the trend and the effects that's having on the IT industry. We also talked about the fact that systems analysts have to consider web-based development environments. And finally, we explained that the systems analyst role in the software development process depends on the specific development strategy that was decided on. The most important factor in choosing a development strategy is normally total cost of ownership. The process of acquiring software involves a series of steps, 6 if you will recall. And also, we just went over the fact that a prototype is a working model of the proposed system, but that it has its limitations, but in spite of those limitations, it's well worth doing.